who will speak on the GCD of n and the nth Fibonacci number. Please, Paolo.
Thank you, Mark. This is a joint work with Carlos Anna, and I'm going to speak about the set of integers which can be represented as the greatest common divisor between some integer n and the nth Fibonacci number. So let me be precise in a moment. Okay, we start with Fn to be the sequence of Fibonacci numbers, which is just the sequence starting with 1, 1, and such that the next element is the sum of the previous two ones. Okay, now we know that Fn and n have many properties. The first one is that a Fibonacci number divides another one if and only if the same divisibility holds also for the corresponding indexes. Another property is that it is a divisibility sequence, which means that the greatest common divisor between two Fibonacci numbers coincide always with the Fibonacci number of the greatest common divisor of the two indexes. Another one is that Fm to the power of 2 divides f of the product between m and n if and only if Fm divides n. Well, there are many structural properties of the relationship between Fn and n, and it has been studied by several authors. And here in this talk, we are going to speak about this set, calligraphic K. Calligraphic K is the set of integers of the form greatest common divisor between n and f of n. For example, the number 10 belongs to the set because it can be expressed as the greatest common divisor between 30 and f of 30. The first elements of the sets are 1, 2, 5, 7, etc. And it is this sequence here. However, just looking at the definition, it is not clear whether an integer belongs or not to this set calligraphic K. And so what we are going to do is, first of all, we have to establish a concrete criterion to check whether an integer belongs or not to this set calligraphic K. And then our main question is, how large is this set? This set here in yellow. Now, to have a concrete criterion to establish whether a set belongs or not to calligraphic K, we have to use the rank of appearance of a positive integer n. So, given n, we define the rank of appearance as the smallest k such that n divides f of k. It is the smallest possible integer k such that n divides f of k. And it is denoted by zeta of n. And moreover, we define L of n to be the least common multiple between n and the rank of appearance of n. Now, given this definition, before we give the concrete criterion, we have to remember that zeta of n, that by definition is the minimum k, such that n divides f of k, is always well defined, and it is always smaller than or equal than 2n. So zeta of n, zeta is a well-defined function. Now the criterion is that an integer n belongs to our set calligraphic K, so can be expressed as the greatest common divisor between an integer and the Fibonacci number of with the same index, if and only if this number n is the greatest common divisor between L of n and f of L of n. So if we want to write it explicitly, if and only if n is equal to the greatest common divisor between the least common multiple of n and zeta of n and the Fibonacci number with the same index. Oops, sorry. Okay. Now, this just gives us a criterion to check directly whether an integer is inside calligraphy K or not. But our question is, how large is this set? And the theorem that we are going to prove is that this set has a cardinality which is at least, up to a constant, the x divided by x. So it has at least the cardinality of primes up to a constant. And on the other hand, it has asymptotic density 0. So there are two, we are going to divide the proof into two parts. First of all, we are going to the lower bound and then the upper. So let's start with the lower bound. And we are going to need a result about the rank of appearance. Now, we remember that the rank of appearance zeta t is the smallest scale such that p divides f of k. And there is a result due to Kubler and Roos, which says that if you define zeta of m as this quantity here, which is simply the relative asymptotic, the asymptotic density relative to the primes, of the primes for which its rank of appearance is a multiple of a positive integer n, where n is fixed. And the theorem of Kubler and Roos says that the asymptotic density relative to the primes exists, and not only exists, but we have an explicit expression, which is this one. So R of m is a constant, which is either 1 or 5 divided by 4 or 1/2 multiplied by this product. Now, if we want to write it explicitly, then R of m is a constant which is more or less equal to 1, but we can rewrite this relative asymptotic density equal to R of m divided by m, because here we have 2 to the e, which divides exactly m, and here we have a minus, multiplied by the product of 1 divided by 1 minus 2 to the minus 2, where 2 divides m. Okay, so we are going to use this result. Now, the first part of the lower bound. To prove the lower bound, we are going to need this lemma here, which is a sufficient condition for a prime to belong to the set calligraphy K. So to be written in the form greatest common divisor between n and f of n. So this lemma says that if prime is a prime different from 3, for which L of Q does not divide Z of P for every prime Q, then P belongs to A. And we remember that L of Q, by definition, is the least common multiple between Q and Z of Q, where Z of Q is the rank of appearance of Q. So our set calligraph K contains at least all the primes which satisfy this sufficient condition. Now we are going to see that the set of primes which satisfy this condition have a positive relative density with respect to the primes. So the lower bound is at least x divided by log x up to a constant. Now we fix y that we are going to choose later, but you fix a real number y, and we define these two sets, P1 and P2. P1 is the set of primes for which whenever Q is in the interval from 3 to y, then Q is not a multiple of zeta p. And moreover, P2 is defined to be the set of primes for which L of Q divides zeta p for some Q bigger than y. So from the definition of P2, we see the relationship with this lemma here directly. And also with P1, because also with the definition of P1, we know that if a prime satisfies this hypothesis in P1, then it is for sure an element of calligraphy K. Okay. So every member which is inside P1 but not inside P2 satisfy the hypothesis of this lemma, so by force belongs to calligraphy K. So we have to estimate the largeness of P1 and the largeness of P2, and to conclude that the cardinality of P, which is a subset of A, is at least x divided by log x. Now, since P by definition is P1 minus P2, we need a lower bound on P1 and an upper bound on P2. Okay, what about P1? We denote by P of y the product of all the primes in the interval from 3 to y, and with mu the Mobius function. Now, with the inclusion exclusion principle and using the result of Huber rules, which says that the relative density of the primes for which zeta p is a multiple of a positive integer admits asymptotic density relative to primes, which is positive and equal to this value here. Using that result, we know that P1, and we remember the definition of P1, is the set of primes for which whatever is Q in the interval from 3 to y, then Q does not divide zeta p. And why this is sufficient? Q is a divisor of L of Q, because L of Q by definition is the least common multiple between Q and zeta of Q. So if you know that Q does not divide zeta p, then by force L of Q does not divide zeta p. Okay, so what is the cardinality of P1 up to x? Now, if you use the inclusion principle, and you let x equal to infinity, whenever x is fixed here, this quantity is exactly equal to this finite sum here. And then later we take the limit with respect to x going to infinity on the left and on the right. And this limit is equal to, by the result of Huber rules, to this sum here. Now remember that y is fixed, but we have to choose it. So it is equal to plus or minus 1 with respect to the square free numbers here. Mu of m, capital Z of m, where m is a divisor of the product of the primes between 3 and y. Well, we can re-express it directly in this form here. This is just by the definition of the Mobius function. And with the result of Huber rules, we know that this is exactly equal to this quantity here. So using the result of Mertens, because this is more or less equal to the product of 1 minus 1 minus q, more or less, then the cardinality of P1 of x is at least 1 divided by log y, which is our constant, which multiplies x divided by log x, whenever x is sufficiently large with respect to y. So this is a lower bound of P1 as a function of y. Remember that here our set P is a subset of A up to the prime 3, where the definition of P is P1 minus P2. So now we need an upper bound on P2. Before we give an upper bound, let's remember the definition. The definition of P2 is the set of primes for which L of Q divides zeta P for some Q which is bigger than 1. And zeta P is the rank of appearance of P. So it is the least positive integer of K such that P divides f of K. And we know that zeta P not only is smaller than or equal than 2P, but for the rank of appearance, we have an additional property, which is that zeta P, the rank of appearance of a prime P, divides either P plus 1 or P minus 1 for every prime P bigger than 5. So we have this property here. This is true for all the primes P. bigger than 5. So let me add here, or better, different from 5. For every prime p different from 5, we have this property. So the cardinality of the set P2 is at most the sum of the cardinalities of the primes for which L of Q divides theta P, where Q is a prime bigger than 1. So now if we use this property here, this is at most the sum of the cardinalities of the primes smaller than or equal than x, this is the same x here, for which modulo L of Q as remainder either plus 1 or minus 1. At this point, we used a classical inequality for primes that the number of primes that gives remainder A modulo M is smaller than 2x divided by phi of m times log of x divided by m, or phi is the Euler function. And moreover, we are going to use also this bound here that I'm going to skip the proof. Well, here we remember again that the definition of L of Q is the least common multiple between Q and Z of Q. And this is a divisor of Q plus 1 or Q minus 1. So Q and Z of Q have to be coprime, so the least common multiple is simply for every prime Q bigger than 5, it's just the product Q Z of Q. Now, if we use both results, we are going to conclude that the cardinality of P2 is upper bounded by this quantity here. X divided by log x by times this quantity that depends on y, and remember that we still have to fix the value y, plus x to the power of an exponent smaller than 1, 7 divided by 8. Now, since the cardinality of, well, P was included in A up to the prime 3, and the definition of P is P1 minus P2. So the cardinality of P up to x is at least the cardinality of P1 minus the cardinality of P2, both up to x. And just using the two estimates, we know that this is the lower bound of P1. And this is the upper bound of P2. Well, or better, they are the constant for which we have the lower and the upper bound. And we know that if we choose y to be a sufficiently large constant, then this factor here, which multiplies x divided by log x, will be a positive constant. So if you fix y, which is sufficiently large, depending on C1 and C2, but C1 and C2 are fixed, then we get that the cardinality of P up to x is at least x divided by log x. But P is a subset of A. So the cardinality of A, and here we can also use bigger than or equal, is at least the cardinality of P, which is at least the order of x divided by log x. And this is the proof of the lower one. Now we are going to prove the upper bound that the asymptotic density of the set capital A, which is the set of integers which can be expressed as the greatest common divisor between k and f of k, is equal to 0. Again, we are going to use a lemma which gives a condition under which a condition the set capital A. And this condition is that if you pick an integer in n, remember that we have to compute an upper bound. If you fix an integer in n, and with the additional property that L of Q divides L of n for some prime Q, then by force Q is a divisor of n. So the condition is that L of Q divides L of n, but this is the least common multiple between n and z of n, and this is the least common multiple between Q and z of Q. But since Q and z of Q are coprime for every prime Q different from 5, we can write if Q is different from 5, that this is Q zeta Q. So this is the condition, which is quite explicit. So if we can find a prime Q for which Q zeta of Q divides the least common multiple between n and zeta of n, then by force Q divides n. So this Q here has to divide this n here. Now the proof is you fix an arbitrary epsilon bigger than 0. And also you fix, I remember that here is fixed, you fix a prime Q with the only condition that it is sufficiently large, meaning that the multiplicative inverse of Q is smaller than epsilon divided by 2. And moreover, we define calligraphic Q to be the set of primes for which L of Q divides zeta P. Now remember that zeta P is a divisor of P plus 1 or P minus 1. And L of Q is Q zeta of Q for every Q different from 5. And using the result of Kubler rules, well, if this is an integer m, the result of Kubler rules says that the set calligraphic Q, which is a set of primes, has a positive relative density in the set of primes. As a consequence, if we evaluate this product here, the product of all the primes in this set, then for sure this converges to 0. So it means that not only we can find a sufficiently large Q, but Q is fixed, calligraphic Q is fixed, and we can find also a sufficiently large Y for which this product is sufficiently small. And we fix Y such that this product, since it is convergent to 0, is smaller than epsilon divided by 2. So all of them are fixed. Okay. Again, we split A into two subsets. This is a partition, A1 and A2. A1 is the set of integers, which can be expressed as the greatest common divisor between k and f of k, with the property that n has no prime factors in Q of y, where Q of y is this set here, is the set of primes for which L of Q divides zeta p. And A2 is just a complement. Now, if n is an integer which is in A2, so it is in A but not in A1, then for sure n is an integer that has at least one prime factor in Q of y, and we denote it by T. And the definition of Q of y, we remember the definition of Q of y is the set of primes for which L of Q divides zeta p. So here we know that L of Q divides zeta p, but if n is in A2, then we know that P divides n. So we know that L of Q divides zeta p, which divides zeta n, which divides L of n. But if we go back to the original lemma, here it says that if L of Q divides L of n, and in addition n is an integer of our set, then for sure Q divides n is a multiple of Q, and Q is fixed, and it is sufficiently large. So in the case of the subset A2, since we know that Q divides n, then all the elements of A2 are multiples of Q. So we can conclude to say that since all the multiples of A2 are multiples of Q, then the cardinality up to X is at most 1 divided by Q. And moreover, what is the cardinality of A1? Well, A1 is the set of integers which have no prime factors in Q of y, and moreover, n belongs to A. But if they have no prime factors inside calligraphic A, then at most they have cardinality x times this factor here, which is the product of 1 minus 1 minus p, again by the inclusion exclusion principle. But we know that both of them are smaller than or equal, are smaller or smaller than or equal, it doesn't change anything, than epsilon divided by 2. So the upper asymptotic density of the set calligraphy K is at most epsilon. Now we go back to the beginning, and we know that epsilon was fixed at the beginning, but it was arbitrary. So the conclusion is that the asymptotic density of A is equal to 0. And this proves the upper bound, that the cardinality of A up to x is small of x. Here we finished, and I want to conclude with essentially one open question, which is, can we find an effective upper on the cardinality of A up to x? And if we refine the question one is, what is the real largeness of the set calligraphic A? Is it true that it is really of the order x divided by log x? And the best possible thing could be, can we find that asymptotic formula? Well, I want to add that I've chosen to present this result because we are trying to work with Carlo on an improvement of the upper bound of calligraphic A up to x, the cardinality of A up to x. And if it should be, Carlo can correct me if I'm wrong, that this is at most x divided by log x to some power c, where c can be computed explicitly as a constant equal to 1. Anyway, we have no idea how to answer question 2 and question 3. And that's all.
Okay, thank you. Any questions for our speaker?
Yeah, regarding the, what A of X looks like, have you done any numerical studies? How far out have you gone if you have, and things like that?
Not that I remember.
Okay.
I thank our speaker again. And the next talk will be in 3 minutes. Thank you.